Okay. Hello guys. So this video is from section 3.1. It's about introduction to functions, relations and functions. Okay. So objectives of section 3.1, it's understand the definition of relation and functions, determine whether equation represent function, using function notation to evaluate functions, use of vertical line test, and determine the domain of the function given the equation. So first, the definition of the relation. Relation is the correspondence between two sets, A and B, such that each element of set A corresponds to one or more elements in set B. Set A we call the domain of the relation, and set B we call the range. So relation is the special correspondence between two variables, usually between x and y. All x elements will belong to the set A, which the definition explains, which we call the domain, and all the outputs, which is the y values, will belong to set B, which we call the range. So each element from set A corresponds to one or more elements from set B. So this is the relation. This is the definition of relation, not a function. And here, example of the relation. We have two sets. Set A, it's the domain. That's the inputs of the relation. Set B, it's the range. That's the outputs. And here we have Adam corresponds with 180 pounds. Patrice corresponds with the output, which is 190 pounds, and Scott corresponds with the output of 180 pounds. So this relation represents three people and their weights. So technically in this mapping, we see that Adam weighs 180 pounds, Patrice 190 pounds, and Scott also weighed 180 pounds. So that's the relation. Adams, three people and they weight. So this is the relation because each input, which each element from the domain, corresponds with one or more elements from set B, which is range. Okay. Now here, when we will talk about this relation, so what happened? They switch. Now the inputs of the relation, it's the weight, and the outputs of the relation are people. So here, this is just the example. Suppose that delivery man was to deliver a package to the roommate who weighs 180 pounds. So he doesn't know the name, but we have the roommate who weighs 180 pounds, and we see that that's been correspond with Adam and Scott. They both weigh 180 pounds. So because there are two people who weigh 180 pounds, there is no way for sure who's supposed to receive the package, Adam or Scott. So this is because the element 180 has two different outputs. It's been assigned to two different outputs from set B. Okay, so this is a relation. However, this relation does not represent the function. So this relation, it's not a function, okay? Because for a function, every element from the domain must correspond to exactly one element from the range. So this is a relation, but not a function, because in function, each element from the domain should correspond with only one output from the range. So here we don't have a function because the input 180 has two different outputs, and that cannot happen in function. Yes, it's a relation, but not a function. So here you guys see on the next slide the definition of the function. So function is a very specific relation such that each element in the domain has exactly one corresponding element in the range. each input has exactly one output. Okay, so here in example 1, we have to determine whether each relation is a function and then find the domain and range. Okay, so let's start working with this example. Okay, so in this example, part A, we have to see if we have a function. So here we have domain. The first set will represent the domain, and the second set will represent range, which is the outputs. So we have the Phoebe. Her height is 5, 5. Amy, her height is also 5, 5, and Kathy, her height is 3, 1. So the question is this relation represent function? So definitely this relation is a function because each element from the domain has assigned only one element from range. So this is a function because each element in the domain has exactly one corresponding element in a range. Okay, so this is a function. Now we have to describe what is the domain. So the domain of this function is the set of all inputs. So we're going to list all the inputs, which is the name of 3 people: Phoebe, Amy, Kathy. So that's domain. Now the range. That's the elements from the set B. That's our output. Is, in our case, 5.5. I'm sorry, 5, 5, and 3, 1. So that's the range. And we're going to do the same type of work for part B. So all the elements from the first set represents the domain. All the elements from the second set represents the range. So we're checking if this relation represents the function. In the function, each input has assigned exactly one output. So 0 has one output 7, 3 has one output 7, -2 has one output 7, 6 has one output 7. So this is the function. This relation represents a function because each input has assigned only one output. So it's okay that all those inputs have the same output. This is a function. Also, you guys, students of this class, and me, we are a function. Every single student of my class belongs to the domain, and the teacher, I'm only one teacher, but each of you has only me as a teacher. Okay, so we are definitely a function, and this is the function. Each input has exactly one output. It's okay that they have the same output. So this relation is a function. And now we have to find the domain. So domain of this function, we're going to list all the elements from the first set I'm just going to organize them from smallest to highest. So it will be -2, excuse me. So when you list the elements from the domain, it's good to put them in order from least to highest. In range, we only have one element of range, which is 7. Okay. So now we're moving to example C. So in example C, you see the set of ordered pairs, and we have to decide if that set represents the function. So the definition of function is that each input has assigned exactly one output. So here we don't have a function because input 3 has two different outputs. We have 3 has assigned output 7, but also 3 has assigned output -4. So here there is definitely not a function because input 3 has two different outputs. So not a function because the element 3 corresponds to two different elements, 7 and -4 in the range. So now we still can find the domain of this relation. So it's not a function. However, it's a relation. So domain of this relation, we're going to list all the first x elements, all the first x coordinates. So domain just lists all the first coordinates, which is x coordinates, and list them from smallest to highest. So the lowest one, it's -4. Then we have -3, 1, 3. So like you see, element 3 repeats. When I'm finding the domain, I'm only listing x equal 3 once. And now range. For range, we're going to list all the y coordinates. And organize them from smallest to highest. So we have -4, 2, 4, 5, 7. Okay. And let's talk about example D. We have to decide if this relation represents the function. So we have to check if each input has different output. And the shortcut will be when you guys have the list of ordered pairs, to check if you have a function, you just have to make sure that the x coordinates don't repeat. So in this case, x coordinates don't repeat, so we definitely have a function. So yes, this is a function. So for the domain, we're going to list all the x coordinates, list them from least to highest. So -1, 0, 1, 2, 3. So this relation is the function in range. we're going to list the y coordinates. And list them from smallest to highest. So the smallest one, it's 2. And there is 2 y coordinates with the y value equal 2, but we're only listing once. And then we have 3 and 5. So like you see, when we list the domain and range, we only list the elements once. Now we can move on to example 2. Understand the definition of relation and function. Use the domain and the range of the following relation to determine whether the relation is a function. Okay. So here what I'm going to do, I'm going to rewrite this graph as a set of order pairs. So it will be just easier to decide if this graph represents a function. So let's rewrite this relation as a set of ordered pairs. So this point has coordinates -4, 5. This point has coordinates -2, 2. This point has coordinates 0, 0. This point has coordinates 1, 4. And this one has coordinates 1, -2. So now it will be easier to decide if this is a function. So to be a function, each element should have assigned only one output, which is one y value. And this relation is not a function because element 1 has 2 different output. So we have one with the y coordinate equal 4 and one with the y coordinate equal -2. So this is not a function. And I mentioned to you about the shortcut when we have 2 points with the same x coordinate but different y values, definitely not a function. So not a function because x equal 1 has 2 different y values, 4 and -2. So we know it's not a function. However, we still can find the domain of this relation and the range. So domain, we're going to list all the x coordinates, so all the first elements, and just organize them from least to highest. So it will be -4, -2, 0, 1. I know that element 1 repeats twice, but we only list that element once only. And range, that will be the y coordinates. So we're going to list all the y values from smallest to high. So -2, 0, 2, 4, 5. Okay, and we only list them once. Okay. So we're moving on. So here is just the summary. So to determine whether equation represent a function, we must show that for any value in the domain, there's exactly one corresponding value in the range. So for any x in the domain, there's exactly one corresponding y value in the range. So example 3 is a little different because in example 3, I'm giving you 3 different equations and we have to decide if which of the equation would represent function, will represent y as a function of x. So I can give you a hint for them, which you guys very quickly can decide without doing any work if given relation represents a function. You will know that you have a function when y variable is being raised to the odd exponent. So example one, it's a function, and I quickly know that because y variable has exponent equal 1. So when y variable is being raised to the odd exponent, always a function. Example 2, b, this is a function, y variable is being raised to the exponent 1, odd exponent, function. Example C is not a function because y variable is being raised to the power of 2, even exponent, so not a function. So hint, if y variable has odd exponent, then the relation is a function. So in example A, they gave you the linear equation in a standard form, and they want you to decide if this is a function. I gave you that shortcut quickly, that y it's been bring to the power of 1 at exponent, so we have a function, so this is function. And also they showing you that you can work with that equation, you can isolate this equation for y, and you're going to see that for any input of x, you always will get only one output. So this is a function. So this equation represents function. Represent y as a function of x. Here, definitely we have a function, because in this equation, variable y, it's being raised to the odd exponent, so it's a function. But technically what that means, that for any x value which you will pick, you only will be able to evaluate one output. So it's a function. Example C, it's not a function. This is what is given. I quickly see that this is not a function because y has even exponent, so not a function. But also what you can do, you can solve this equation for y, and like you see the outputs, which is y, will become positive or negative square root of 6 minus x plus 3 to a second power. So that means, let's say if you will make x equals 0. So to evaluate y, you will get two output for each input. We're going to replace that x with 0, and we have 6 minus 3 to a second power. So y will be equal positive, negative. Oops, it cannot be 0. Sorry, we didn't talk yet about domain. Let's make it negative 3. So then we have 6 minus negative 3 plus 3, so that will end up to be 0 to a second power. So we have square root of 6, so that means we have y equals square root of 6, and y equal negative square root of 6. So this is not a function because for each input, we'll have two different outputs. So like you see, that's not a function. But you don't need to do all that work for homework. You can quickly realize that the y variable has even exponent, so not a function. To be a function, y variable has to be raised only to the odd exponent. So we're moving on. Function notation. So function notation, instead of using variable y, letters such F, G, or H, and others, but this is the most popular, they will represent the function. So they will represent the name of the function. If we want to name a function f for any x value in the domain, we call the y value or function value. So we're going to use the function notation, which is f of x, can be g of x, can be h of x. So we read that f of x, f is the name of the function, x shows you the input, independent variable. So f of x will be the function notation. The meaning of f of x will calculate the value of the function, which means that f of x represents the y value. F of x has the same meaning as a y value. Just very important to not make a mistake. This is not the same as f times x. This is just a function notation. F of x. That means the name of the function is f. Input, which is the domain of this function, will be the x elements. And the meaning of f of x is y value corresponding to the given x. So on the next slide, I'm showing you how to use function notation to evaluate the function. So we have a function. Again, originally that was y equal 3 over 2x plus 5. Since we're dealing with functions, so we replace y with the f of x. Okay. So we want to evaluate this function for x equal -4, x equals 0, 1, and -3. So we substitute x from the function equation with the given value. So we want to evaluate function value when x is equal -4. We're going to substitute x from the equation with -4. So we have 3 over 2 times -4 plus 6. We end up with 0. So we evaluate the function f of -4 is equal 0. That means we have a point which belongs to this function. X coordinates -4. That f of x, that's our y value. So y coordinates equals 0. And you will do the same thing for other x values. We need to evaluate the function when x is equal 0. We're going to substitute x with 0, calculate, we end up with 6. So technically, we have a point 0, 6, which belongs to this function. X is 0, the output, which we evaluate, it's always y coordinate. And we're doing the same thing for 1 and -3. Okay. And here in this slide, you just see that we just plugging in those points and they represent the graph of the straight line. That's our function. Okay. So next example. In next example, we need to rewrite given equation using function notation where y is a function of x, then answer the question following each equation. Okay. So part A, this is our equation, and they're asking you what is the value of f of x. So first what I'm going to do, I'm going to rearrange this equation and solve it for y. So first, solve for y. So we're going to take the equation 3x minus y equal 5, isolate y. So we'll subtract 3x from both sides. We have negative y equal negative 3x plus 5, and then divide each by -1. Okay, so now we have it, y is equal 3x minus 5. So what we're going to do, we have to use the function notation. So y has the same meaning as f of x. So this is function f of x equal 3x minus 5. And now, when we have that function notation, we can evaluate the function f of 4. So we're going to replace x with 4 and we're going to evaluate that. So f of 4 equal 3 times 4 minus 5, and that will give us 7. And we'll do the same thing for part B. First, we have to use the function notation. So I'm going to rearrange the given equation and solve for y. Okay, so we need to isolate y. So I'm going to subtract x squared from both sides. Or you know what? It will be just easier, actually, and faster to move that negative 2y to the other side. So I will add 2y to both sides. We're getting x squared plus 1 equal 2y. And to isolate y, divide each by 2. So we have x squared plus 1 divided by 2 equal y. Okay, so now the function notation is replace y with f of x. So we always replacing y with f of x. And now they asking, does the point negative 2 comma 1 is on the graph of this function? Okay, so what we're going to do, I'm going to replace x with negative 2, and I'm going to check if the output will give me 1. So let's check if f of negative 2 is equal 1. So we want to check. Okay. So let's evaluate f of negative 2. We're going to replace x with negative 2. So we have negative 2 squared plus 1 divided by 2. This is 4 plus 1, which is 5 divided by 2. And we're getting 5 divided by 2. And this is not equal to 1. Okay. So since f of negative 2, it's not equal to 1. Okay, when we evaluate, so if that point will belong to the function, we should get 1. However, it's not true. That means point negative 2 comma 1 does not belong to the function. Point does not lie on the graph. Okay. Next example, they want you to rewrite given equation using function notation. So technically we need to solve for y, then answer the questions about this equation, about this relation. So solve for y. So that will be y equal negative 7. So then the function notation is f of x equal negative 7. So we have function notation. And now we can answer the question, what is f of x when x is 3? So find f of 3. And since here our function doesn't have an x, so that means for any input, the y value always will be equal -7 because this is the horizontal line. So f of 3 will be equal -7. Okay, because this is, again, horizontal line. So for any x value, the y coordinate always will be equal -7. And this is a function, yes, each input will always have the y value equal -7, which is just one output. And we're going to work with example 5. We have function f of x equal x squared plus x minus 1, and we need to evaluate the function. So first, f of 0, we're going to replace x with 0. And that will give us -1. And f of -1, we're going to replace x with -1. So we have 1 plus 1 minus 1, 2 minus 1, we're getting 1. Oh, excuse me, it should be -1 here. So then that will be 1 minus 1 minus 1, so the solution will be -1. Okay. And then still problems with evaluating. So we're still working with the same function f of x, which is equal x squared plus x minus 1. And in this problem, we need to evaluate f of x plus h. So that means where we used to have an x, we're going to substitute x plus h. And we're going to simplify that. So x plus h to a second power. This is the same as x plus h times x plus h. Then plus x plus h, you can remove the parenthesis, minus 1. So FOIL x times x will give us x squared. X times h is xh. H times x is xh. H times h will give us h squared plus x plus h minus 1. Simplify, combine like terms. Xh plus xh will give us 2xh plus h squared plus x plus h minus 1, and we're going to leave it that way because there's no like terms which we can combine. And we will do the same thing for part D. Part D, actually, we have to evaluate this quotient. Okay. So first, this is a longer process. So first, we already evaluate f of x plus h, which is this. So here to calculate that ratio, I'm going to substitute f of x plus h with x squared plus 2xh plus h squared plus x plus h minus 1 minus f of x. F of x, we're going to copy the function equation and we will divide each by h. Okay. So first, f of x plus h. This is our f of x plus h. So let's substitute. So we have x squared plus 2xh plus h squared plus x plus h minus 1 Now, minus, I just have to move it that way, f of x. So f of x, it's our function. So let me just plug it in. So x squared plus x minus 1. And we need to divide each. So I'll just put it that way. We're going to divide each by h. So let me just rewrite it. Let me put all of it together. Here, we'll just move it. So x squared, I'll just continue here. F of x plus h minus f of x divided by h. So let me copy that f of x plus h. X squared plus 2xh plus h squared plus x plus h minus 1 minus, and now I'm subtracting this. So that means each original sign, which you see in the parentheses, because we're subtracting, that means technically we're multiplying by -1, will change to opposite. So that will be negative x squared, that will be negative x, and that will become positive 1. And we divide each by h. So now we have to simplify, combine like terms, that should simplify. So positive x squared, negative x squared cancel. Then we have positive x, negative x cancel. -1, positive 1 cancel. And we end up with 2xh plus h squared plus h divided by h. And now I'm going to divide each term from numerator by h. So that will be 2xh divided by h plus h squared divided by h plus h divided by h. And we're getting 2x plus h plus 1. And this is the answer. Okay. Next, we're going to move on to vertical line test. Vertical line test, it's very easy test. You're going to use it when you see the graph of the relation or function without the equation. And if we have to figure out if the given graph represents the function. So the vertical line test tells you that if and only if there's no vertical line intersect the graph more than once. So what that tells you? That just tells you that given graph will be a function if you're going to draw the vertical lines, and you can draw many vertical lines, but each time when you draw the vertical line will intersect graph once only. So that means this graph represents the function. So here we draw vertical line, the vertical line intersect graph once. Okay, we good. Here, vertical line intersect graph once only, we good. And all the time when we draw those vertical lines, each time vertical line intersect graph once only. So if you have a situation like that, this is wrong because I don't know why it's like that. This is wrong. This is a function. It's a function. This is a function. Here is, let me just fix that. It's not a function. This is not a function in this problem, because when we're drawing the vertical line, like in this case, the vertical line intersect my graph more than once, so it's not a function. Okay. So let me just write vertical line test. If vertical line and that vertical line, it's the imaginary vertical line which we create, intersect graph only once, the graph is a function. Okay. So if vertical line intersect graph only once, very important, only once. So then the graph represents a function. That's why in this case, not a function. So let's just quickly do the examples. So those will be quick. We're going to use the vertical line to determine to which of the following graph represents graph of the function. So part A, I'm drawing vertical lines, and all the time vertical lines intersect graph once only, so that's definitely function. In part B, I'm drawing vertical line, and so far all the time vertical line intersect graph once only, and look what happened here. Here we also good because this vertical line intersect graph once only. We know that when you have an open circle, so that's a hole. So that point does not belong to the graph. So this is also a function. For part C, I'm drawing the vertical line. Here my vertical line intersect graph more than once, so not a function. Okay. So let's continue. Next, in this section 2.1, they introduce the polynomial function. So the shortcut of polynomial function, it's going to be a function when our variable, it's going to be bring to the power greater than 1. So like 2, 3, and so on. So in this notation, an minus 1, an minus 2, a1, and a0, they just represent the coefficients of variable x. A0, it's a constant. Okay. And the domain of all polynomial function, it's always the set of all real numbers from negative infinity to infinity. So example of polynomial function. Example will be f of x equal to x to the power of 5 plus 3x to the third power plus 2x plus 7. That's for example. So like you see, this is the polynomial function because our variable x has the highest exponent 5, which means power greater than 1. And the degree of the polynomial function, it's always the highest exponents of your variable. So in this case, this is polynomial function, and degree of this function is equal 5, which is the highest exponent. Now, rational functions, that's the functions which will have a ratio of two different expressions. So technically, we're going to see a fraction. So you may think about rational function as two different functions. Function g will represent the numerator, function h will represent the denominator. So the ratio between two different functions will give us the rational function. And very important about the domain of rational function is the set of all real numbers except h of x equals 0, not equal to 0. So technically, when we have rational functions, that function only will work if we're going to give the condition that the denominator h of x is not equal to 0, because we can never ever divide by 0. Root functions, so that's the function when you're going to see a root. N represents the index of the function. So when n is integers such that n is greater or equal to. So when we're talking about root function, we can divide them into two different functions. The one when the index of the root is even number, like square root functions, the one which the index will be 4, 6, and so on. When we have root functions with even index, the domain of this function will be the solution of the inequality. you have to give the condition that the expression under square root is greater or equal 0. And when we have a root function with add index like 3, 5, and so on, like a cubic function, for example, the domain of those functions will be the set of all real numbers. So here on the next slide, you have a table which will help you to classify the function by polynomial and how to find the domain. So polynomial functions, domain, all real numbers. Rational functions, we have to give the condition that h of x is not equal to 0. Root functions, we break them into two functions, the one with even index. To find the domain, we have to solve the inequality g of x greater or equal 0. When our root function has add index, the domain will be the set of all real numbers. And our next example, we need to classify each function as rational function, root function, or polynomial function, and then find the domain of each using interval notation. Okay, so part A, this is polynomial function. Polynomial function. Again, polynomial function, you see that we have variable, bring it to the exponent higher than 1. Part B, this is rational function because we see the ratio, we see the fraction. Part C, we have root function. Root function. So we classify each of them. Now we're going to find the domain. So here the domain, since it's polynomial function, it's just going to be interval from negative infinity to infinity. Part B, in part B, we have rational function. So to find the domain, we have to give the condition that the denominator is not equal to 0. Okay. So not equal equation you solve like equal to 0. You want to factor that. So this is the same as x minus 3 times x plus 2. I factor that using AC method, not equal to 0. That means x minus 3 it's not equal to 0. X plus 2 is not equal to 0. That means x cannot be equal 3. X cannot be equal negative 2. So here, the domain is the set of all real numbers except 3 and negative 2. So if I will ask you to graph it, this is x-axis, which represents the domain. So our domain is any real number except negative 2 and 3. So our domain will be the union of three intervals. So the domain, we have interval from negative infinity to negative 2, union. Then the interval here from negative 2 to 3, union, and then from 3 to positive infinity. So again, we have union of three intervals because the domain, it's any real number except negative 2 and 3, because when x is equal negative 2 or 3, when you plug it in into x values from the function notation, the denominator will be equal 0. And we know that we never ever divide by 0. Now, part C, we have root function, index, and it's equal to, so this is the square root function, so even. So that means to find the domain, we're going to solve the inequality. x squared minus 2x minus 8 has to be greater or equal 0. So to solve this inequality, we have to factor this quadratic. So when you factor this quadratic, you will end up with x minus 4 and x plus 2. So I use the AC method. So I need to find two numbers which by multiplication will give me negative 8. So negative 4 times 2, it's negative 8. And the same two numbers by addition has to give you b. So negative 4 plus 2, it's equal negative 2. So we're solving greater equal 0. So to solve this inequality, you want to find zeros. So x minus 4 make it equal 0. X plus 2 make it equal 0. So zeros are maybe not that way. So that will be x equal 4 and x equal negative 2. Okay. And now to solve this inequality, depends how you guys learn it in previous classes, but the way I used to teach to solve inequalities like that, you're putting negative 2 on the number line and you're putting 4 on the number line. Since we're solving inequality greater or equal, so those solutions, when I make that each factor equals 0, so negative 2 and 4 will be part of the solution because we have equal sign. And now I'm checking which interval will satisfy our inequality. Okay, so you can break this down like into 3 intervals and just pick any number from each interval. So here I will pick x equal negative 3. And then I'm going to replace negative 3 where I used to have x and see if I will get the number which is greater or equal 0. So we have negative 3 minus 4 times negative 3 plus 2, and I'm checking if this is greater or equal 0. So we're having negative 7 times negative 1, and this is definitely greater or equal 0 because we're getting 7, which is greater or equal 0. So that means yes, this interval will satisfy the solution of this inequality. Okay. And I will do the same thing I'm going to check if interval from negative 2 to 4 is the solution of the inequality. So I will pick any x between negative 2 and 4. So here I will pick x equals 0. And now I'm going to replace this x with 0. And I will check if it satisfies the inequality. So we have 0 minus 4 times 0 plus 2. And I'm checking if this is greater or equal 0. So this is negative 4 times 2 greater equal 0. We have negative 4 greater equal 0. This is false. So that means this is not part, that interval, it's not part of our inequality. Okay, so let me erase that work. This is just checking. And next what I'm going to do, I'm going to pick, I'm going to pick any x from the interval from 4 to positive infinity, and I will check if, let's say I will pick x equal 5, and I will check if our inequality is true for any x from the interval from 4 to positive infinity. So here I'm going to pick x equal 5. You can pick 100 if you wanted. So let's replace x with 5. So we have 5 minus 4 times 5 plus 2, and I'm checking if this is greater or equal 0. So we have 1 times 7, and this is definitely greater or equal 0. Since yes, this is true, that means this interval is the solution of the inequality. So when you're done with checking which intervals satisfy the given inequality, we have it. That means the domain of this root function will be interval from negative infinity to 2, negative 2. I'm including negative 2 because our inequality was greater or equal, union, and interval from 4 to positive infinity. Okay. So that's what we're doing when we have root function with even index. And I have part D. Here we have root function with add index. So when we have a root function with add index, that means domain is the set of all real numbers. So we don't need to do any work. Domain will be from negative infinity to infinity because add root function with add index, the expression under square root can be positive, can be negative, but also can be 0. And the last one. So here, what we have root function. This is more work here. We had root function with even index. Okay, so we have root function with even index. So we have to, first of all, and also under the root, we have a rational expression. So first of all, we have to give the condition. So here we have to give the condition that x squared plus x can never be equal to 0. Factor x out, so that will be x plus 1 never equal to 0. That means x cannot be equal 0 and x cannot be equal negative 1. Okay, so we have two conditions here. And next, what we need to do, we need to give the condition that the expression under radical, it's positive number. I'm not sure if I will have a space here. So I will just continue here. So next, we need to give the condition that x minus 2 divided by x squared plus x, it's greater or equal to 0. Okay, so here when you guys have to solve inequality, rational inequality, so when we're dividing the numbers, we have to get, when we're dividing those two expressions, we have to get positive answer. So you can solve that the same way as x minus 2 times x squared plus x greater equals 0. Okay, so just factor. So we have x minus 2. We factored already that x squared plus x is the same as x times x plus 1 greater equals 0. So to solve this inequality, make each factor equal 0. So x minus 2 equals 0. That means x is equal to x equals 0. And x plus 1 equals 0 means x equals negative 1. So we make each factor equal 0. And we're going to do the test the same way. So we got negative 1, 0, and 2. That's the x. Now, here it's very important. Because in the denominator we have that x squared plus x, so we gave that condition that x squared plus x cannot be equal 0. So for x equals 0, that cannot be that x equals 0 cannot be in the domain, and also x equal -1 cannot be in the domain. That's why I keep it circle open, because that will make the denominator equal 0. Now x equal 2, that comes from numerator, so that can be 0. So I'm going to keep the circle closed because we're solving inequality greater or equal. So only x equal 2 will be part of the solution. For 0 and -1, I keep circle open because they come from that denominator, and denominator cannot be equal 0. You can quickly see that when x is equal 0, we're getting here 0 plus 0. So we're dividing by 0. So that's why I keep the circle open. When x is equal -1, when you plug it in, we're getting 1 plus -1, which is 0. So that's why we cannot have x values equal -1 and 0, and you see those circles open. And now I'm going to do the test like before. I'm going to pick x's, any value from each interval. So I'm going to pick here x equal -2, and I'm going to check if interval from -infinity to -1 satisfy our inequality. So let's just plug it in for x -2. So we have -2 minus 2 times -2 times -2 plus 1. And I'm checking if I will get my solution will be greater or equal 0. So you have -4 times -2 times -1. And we're checking if this is greater or equal 0. We're getting -4 times -2. It's +8 times -1. That will be -8. It's definitely not greater or equal 0. So since this is false, this interval is not part of the domain. Next, I'm going to pick any x value between -1 and 0. So I will pick x equal -1/2. So let me erase that. And I'm going to replace each x with -1/2. Okay. So we have -1/2 minus 2 times -1/2 times -1/2 plus 1. You can change to a decimal if you want it. So we have -1/2 minus 2, so that will be -2.5, which is -5/2 times -1/2 times 1/2. So here I already know that the solution will be greater or equal 0 because two negative numbers will become positive. So this is true. Since this is true, in our domain will be the interval between -1 and 0. And next I'm going to check if interval between 0 and 2 will work. So I'm going to pick x value between 0 and 2. So let's pick x equal 1. So I'm going to replace each x from the inequality with 1. So we have 1 minus 2 times 1 times 1 plus 1, and we're checking this is greater or equal 0. So we have -1 times 1 times 2 greater or equal 0. We end up with -2 greater or equal 0. Since this is false, so this is not part of our domain. And the last part, I'm going to check if interval from 2 to infinity, it's our domain, satisfy our inequality. So I will pick the x value bigger than 2. Let's pick x equal 3. Plug in into our inequality right here and check if we end up with a true statement. So the same thing, I'm going to replace each x with 3. So we have 3 minus 2 times 3 times 3 plus 1. And we're checking if this is greater or equal 0. So we have 1 times 3 times 4. We definitely end up with a positive number. So this is true. That means interval from 2 to infinity, it's part of the domain. Okay, so now domain of this function is interval from -1 to 0, union, and we adding second interval, 2 to positive infinity. Okay. So this is the end of section 3.1. I'm going to share the notes with you guys on Canvas.